Okay, good day, guys. Today I'm going to be solving problems involving stress, strain, Hooke's law, and strain energy. So first of all, copy down this question. The question says a square steel rod of 40 millimeters by 40 millimeters is to carry an axial load of 200 kilonewtons. Calculate the stress, the deformation in the length, the strain energy if the Young modulus is 4.28 times 10 raised to the power 8 kilo Newton per meter square. The length of the material is 100 millimeter. So now we're going to solve this problem. So first of all, we're going to write our given parameters. So we have our given parameters. So first of all, we are given the dimension of the steel rod, which we say that is of the dimension of the steel rod, where we say that is of 40 millimeters by 40 millimeters. So this is the dimension of the steel rod. So if you do this, you're going to have now this is in millimeters, and we know that millimeters is 10 raised to the power negative 3 meters. Very, very important. In the beginning of our video, I took my time to explain that. So now we're having 4 t times 10 raised to the power negative 3 times 40 times 10 raised to the power negative 3 meter. So we have here as our area equals to 1600 times 10 raised to the power negative 6, which will result to 16 times 10 raised to the power 2 times 10 raised to the power negative 6. So you have 16 times 10 raised to the power negative 4 meters squared. So we can go further to simplify this, that our area is 1.6 times 10 raised to the power negative 3 meters squared. So this is the first parameter they gave us, which is the area of this square steel rod. It's a square because its length and breadth are equal. Now take note that we are given the next parameter we are given is the length, who we say that is 100 millimeters. When we do the same thing with D, you're going to have this as 0.1 meters. So what are we given next? We are given the Young modulus, which we say that is from the equation is 4.28 times 10 raised to the power 8 kilo Newton per meter square. Now what I'm doing is here, I'm trying to bring down the unit in this right proportion because it's very, very important you do that. You can see kilo here and you can see 10 raised to the power 8. When we do that, we know that this is 4.28 times 10 raised to the power 8 times 10 raised to the power 3, because kilo is 3. So this will result to 4.28 times 10 raised to the power 8 plus 3 is what? 11 Newton per meter square. This is the Young modulus. We earlier said that in our last video that the Young modulus units and stress unit are equal. So you can check that. You can see that is Newton per meter square. What are we giving next? We are giving okay, I think that is all. Okay, we are giving the load. Very, very important. The load is a great factor in calculating stress, strain, and Young modulus. And we are giving the load as 200 kilo Newton, which will result to 200 times 10 raised to the power 3. This is 1, 2. So you're going to have 2.0 now, or the same thing as 2 times 10 raised to the power. This is 2. So we're having 2 times 10 raised to the power 3. This will be simplified to 2 times 10 raised to the power 2 plus 3 is what? 5. Very, very important. Okay, now, so this is our given parameters. So we are going to start by solving this question. So we have solution. So the first thing they say you should calculate, which is they say you calculate the stress. So we have the stress. The stress is signified by this, more like sigma, which is P over A. Very, very important. So we have our stress as our load as 2 times 10 raised to the power 5 all over the area, which we say the area is 1.6 times 10 raised to the power negative 3. So with that, we're going to have 2 over 1.6. So we're having times 10 raised to the power 5. Negative 3, when it comes up, it will become positive. So we have plus 3 here. Now this will result to a value which is 1.25 times 10 raised to the power 8. Now, so we can say that our stress is equals to 125 times 10 raised to the power 6. Now, take note, 10 raised to the power 6 is mega. So we can represent our stress as 125 mega Newton per meter square. Very, very important. So we have calculated our stress. We see that this is load per area. Very, very important. So our stress is 125 mega Newton per meter square. The next thing they say we should calculate is the deformation in length. Deformation. Now earlier we said that deformation is the same thing as extension. It's also the same thing as elongation. Now it is signified by this, where we say that is what? In terms of strain, we say that in terms of strain, from strain is given by this symbol. We say that strain is what? Deformation over original length. We have the length of this, which is 0.1 meters. We don't have the strain and we don't have the elongation. So what relationship can you coin to look for this? Of course, from very, very important, you coin this relationship. We say that the Young modulus is what? The stress over the strain. Now, when we substitute this, we have P over A for the stress divided by extension over length. When we do this, we did that in the last video, we're going to have so we have the deformation equals to the load is 2 times 10 to the power 5 multiplied by 0.1 all over the area, 1.6 times 10 to the power negative 4. Of course, that's what we have here. Okay, wait, this is okay, negative 3. Very, very important. Negative 3 multiplied by the young modulus, which is 4.28 times 10 to the power 11. This is going to give us a 2.9. Let me get that value. So we have 2.92 times 10 raised to the power negative 5. Okay, now take note, negative 5 meters. So this is our value for the extension. Now we are going to calculate the next thing to calculate here is the strain. So we have number 3. Okay, is number C. Yeah, this is C. So we have C to calculate the strain, which is signified by this. Now the strain we said earlier is what? It is the deformation at the original length. So we have deformation over original length. So we have the deformation as 2.92 times 10 raised to the power negative 5 over 0.1. Now 0.1 can be represented as 10 raised to the power negative 1. So we can say that this will be 2.92 times 10 raised to the power negative 6. Now this is the strain. We said that is a dimensionless quantity. We said that earlier in the beginning of the video. So now we have calculated the strain. The next thing to calculate in that problem is what? The strain energy. So we have the strain energy. Now we said from strain energy, we derived that formula. We said that the strain energy is what? Signified by U. It is equals to the square of the strain, the area multiplied by the length, all over 2E. Now, this is the formula for the strain energy equation. So we're going to substitute our values. So first of all, we had our stress to be 125. So we have 125 times 10 raised to the power 6. We had our area to be 1.6 times 10 raised to the power negative 3. We had our length to be 0.1. All over, we have 2. So we have our 4.28 times 10 raised to the power 11. So now our strain energy is gotten and is given by this symbol. We have 2.95 joules. So this is our strain energy.